So this is going to be a brief presentation on the forces and acceleration of an object that is on an incline or an inclined plane. So when an object is on the weight still acts exactly downward like it always does. So mg will be an arrow downward, or if you call it W, or if you call it F sub g for gravitational force, the weight will always be downward. The normal force is perpendicular to the surface, not always straight up, but perpendicular to the surface. So the normal force will go off like this. If there is a frictional force, and I think in most of your inclined plane problems there's not, but if this object is sliding down the incline, the frictional force will be along the incline upward. Now, it's important that we divide the weight into its two components, and they're listed here. This is what we call the parallel component of the weight, the component of the weight that is along or parallel to the incline. And this is what we call the perpendicular component of the weight. It is the component of the weight that is perpendicular to the incline. This angle theta is equal to this angle theta here. And so if you look at the rectangle that the components make, this side of the rectangle is equal to the parallel component. And since it's the opposite side of that, opposite the angle, the opposite side of that triangle, then it is equal to the hypotenuse, which is mg, times the sine of the angle. So that's where we get mg sine theta. And this side, the perpendicular component, is the adjacent side, and so it is equal to the hypotenuse times the cosine of the angle, or mg cosine theta. So just to restate it, the parallel component of the weight is equal to mg sine theta, and the perpendicular component, parallel to the incline and perpendicular to the incline, is equal to mg cosine theta. It's also worth noting that the normal force is equal and opposite to the perpendicular component of the weight, and so if you ever do need to know what the normal force is, it is also equal to mg cosine theta. Okay, to work a problem with an object on an incline, a 50 kilogram block slides down a 30-degree incline. So here's our incline, and it is 30 degrees. We have an object on the incline, and it is 50 kilograms. So I drew a free body diagram. Its weight is downward. Its normal force is perpendicular to the surface. And when we draw the components in, we use dotted lines because they're not new forces. They're the weight, but they're components of the weight. That's the perpendicular component, and that's the parallel component. And when we look at forces, we don't do X and Y anymore. We look at perpendicular to the incline and parallel to the incline. And since the object's sliding parallel to the incline, that's the forces that we're going to look at. So the sum of the forces along the incline, or parallel to the incline, is equal to, well, there's that parallel component of the weight, that force right there, and then there's no other force. There's no friction acting, so that's the only force. And that equals ma. The sum of the forces equals ma. Well, as we said in the previous slide, the parallel component of the weight is mg sine theta, and that is equal to ma. Well, if I solve for the acceleration, I would divide both sides by m. So the acceleration of an object down the incline is simply equal to g sine theta. And you might want to remember that. It'll save you having to work this out each time. If you have an object sliding down a frictionless surface, its acceleration is equal to g sine theta. So in this case, it's 9.8 times the sine of 30 degrees, which is 4.9 meters per second squared. And I thought I had another slide to present, but I don't. So that's how you find the acceleration of an object on the incline. If you remember, if it's frictionless, the acceleration is just g sine theta. Save yourself some time working this out. Thanks for your time. I hope you found this helpful.